we're coming to the end of the course. There's only a couple weeks left. As you see, last class coming on May 13th, so maybe 4 or 5 weeks yet. And we're going to talk about 14 today. Oh, well, I thought we were doing 14 today. Looks like we're doing 13. Let me open that up then. Let me refresh this page. I'm already confused. All right. That's what I thought. We already did 13. There, now I feel better. Today is 422. It is 422. Okay, we're doing chapter 14. And chapter 14 turned out to be pretty long, so I split it into 2 pieces. We're going to do the first 3 sections today and the rest next week. Okay, by the way, there are a lot of special events. This weekend is B-Side San Francisco. If you're interested, if you're interested in security, this is fun. There's a Hack the Bay event on Monday, which will also be fun. And RSA is coming up, and RSA is one of the main conferences in cybersecurity. It's really big, and you can get a free expo pass by just Googling for one. And if you're a college student, you can go for free on Thursday. So these are all things you might want to consider going to. If you go to any of these, they're worth extra credit, and they're all good opportunities to learn what's happening and look for jobs and stuff. Yeah. However, let's carry on to chapter 14. Now I feel better. Good. All right, so the issue here is for a long time, up until maybe 8 years ago, they kept trying to make processors faster and faster. The main thing they worried about was clock speed. There was a huge big deal when AMD made the 1 gigahertz clock before Intel did, and so on. So people really thought more and more processor speed is what you want. But what turned out is they hit a limit there. They couldn't keep increasing processor speed. And what I've been told, although I'm not an expert in this, is the fundamental problem was that the chips would overheat, and running them any faster would cause them to melt. And so what they found was they couldn't make them faster, but what they could do was put more processors on a chip by making them smaller. So we moved into parallel computing, where now we all have multi-processors, and the problem is it's not simple to write code that will run faster on multiple processors. Normal code just has statements that execute in order. You have to do line 10 before you can do line 11. So having multiple processors doesn't benefit you any. So this is the issue. How are we going to make code that actually benefits from the modern world of multi-processors? So we're going to do the first 3 sections this time and the rest next time. So the processor is any circuit that does computation, but for us it's CPUs we're doing, and a multi-core processor is what everybody has these days, a processor of multiple compute cores. And a core is an arithmetic logic unit with registers and some cache that can run a program. So there are different things that can limit your performance. Memory is much, much slower than the processor, so that's a problem. Memory is a bottleneck, so if you are doing something that accesses memory a lot, then the speed of memory, read and write, is your limitation. And if the processor gets faster, that doesn't improve the performance of your program significantly because there's different bottleneck. There's also power wall. Like I said, the processor's temperature and power consumption are a problem. So this will make it more expensive to heat and cool the system, or to power and cool the system. And a lot of people say this is now the dominant concern, and I've certainly read articles that say this is the main reason why we expect to move off of Intel-compatible processors to ARM-compatible processors, for the same reason portable devices and cell phones did this long ago, because they give you more performance with less heat and battery power consumed. All right. Anyway, all right. So then, of course, there's GPUs. GPUs are special graphics processing unit, and the cores are simpler and do not have as much of an instruction set, but they can do certain kinds of computations very fast, and they typically have thousands of cores. So that's many-core computing, which we're not going to be discussing here, but that's where a lot of people go. If you can actually manage to do what you need to do on a GPU, then you can really make it a lot faster with these vast number of cores. And that's for things like Bitcoin mining. Or not Bitcoin mining anymore, but anyway, cryptocurrency mining can be done on GPUs and is much, much faster. So if you do the lscpu command in Linux, it will show you information about your processor. And for us, the important information is the number of sockets, the number of CPUs per socket, and number of threads per core. So this is my virtual machine, or I think this is from your book. This book had 1 socket with 4 cores per socket and 2 threads per core. So the actual number of physical cores is 4, and there are 8 virtual cores, which is 2 threads per core. This is called hyperthreading. One processor core can run 2 threads at the same time, although there is some resource contention, so having 2 threads per core and 4 cores is not really as good as having 8 cores, but it's better than having only 4 cores. All right, and that's what we have here. And so these days, a lot of machines have performance cores and efficiency cores. I know mine do. And so the efficiency cores consume less power, but they run slower. The performance cores have higher clock speed, but consume more power. So you can, in principle, have software that decides which of those to run on, although we're not going to write that kind of software today. But that's another issue. So to program your multi-core system, if you have you have to consider context switching. Now what happens is, if I have a single core system, and then I have multiple processes, 5 processes running on a system with only 1 processor, then what happens is there's a period of, the first process gets a period of time, then it decides to let somebody else have time, the second process will run, then this one, then this one, then that one. In some order, they will each get a time slot. And so it'll take some total amount of time to get the job done that was done with 5 processes. And each of these switches costs you some overhead. To move from running process 1 to process 2, you have to save the condition of process 1, the registers and associated data, save it somewhere, and then restore the saved data to resume process 2 where it left off, and then save it here. So this is called a context switch. When you move from one task you're performing and begin to do a different task, there is a cost involved. All right, so CPU time is the total amount of CPU time used to do the process. Wall clock time is the total time you'll see on the wall clock from the start to the end. And this is often significantly longer than the CPU time. For example, if I only care about process 1, which is like my browser loading a page and there are other processes going on, I'll see this much time consumed when the CPU time was even less, because the problem is I didn't get to use the CPU and monopolize the CPU for all that time. I only got a fraction of the CPU's time. So that's one issue. In a 2-core system, if you have those same processes, then these 2 can go at the same time, those 2 at the same time, and so on. So the actual total amount of time to complete all 5 processes is, the wall time is decreased. But the CPU time is just the same. We had just as much CPU time consumed on all these different cores. We were just able to use 2 cores at a time, so we saved time, saved wall clock time. So threads are what we want. And so you'll have your process one process, which is one program you might run, like a browser. It will then have 2 threads or more threads, and each thread will have its a stack, and they'll have a stack and heap area available, and at runtime it will create separate stacks for the 2 threads, one for thread 0 and one for thread 1. So if you're only running 1 thread, it'll look like this. If you have 2 threads, it'll make 2 separate stacks, but they'll both share the same heap, and they'll both share the same global variables and the same instructions and the same linking to the operating system. So they have 2 copies of it here, and their stack variables are separate, not connected, but these other things are connected. So that's what threads are. So if you consider this scalar multiplication task, where what we're going to do is just going to take an array and we're going to multiply every element of the array by a number. So it's a very simple task. And so if the array has n elements, if we want to make a multi-threaded version, we're going to have to create t threads and give each one of them a subset of the job to do, which would be n over t elements, and then tell each thread to do this job. So if you had 4 threads, then a single core CPU would have to do the threads one at a time. So it would not benefit in any way from being threaded. You could just run it all in 1 thread and you'd actually be faster because you wouldn't have the context switch time loss. But in a dual core CPU, it could be much faster. If the context switches don't waste much time, it could in principle be up to 2 times faster. In practice, you usually don't get that much because there is some overhead. All right, and if you had 4 threads, it could be a lot faster. All 4 threads could in principle progress independently. All right. So POSIX is Portable Operating System Interface. This is a Unix standard. So if POSIX code is code that should run on any Linux or Unix system, that's the idea. So POSIX threading looks like this. And so I've got it here. Let me just bring it up. I should have my machine going. Here we are. All right. So let me clear and make the font bigger. All right, now do ls, and this one is threads1, so let's just cat threads1 .c. All right, so what we have here is, first I have to include some libraries, standard IO and standard library, and then I include this library pthread.h, which we haven't used before. That contains the thread functions. Now you have a function which is what's going to be run for each thread. In this case, it's hello world, and all it's going to do is print hello world I am thread ID, and it's going to get fed a parameter which is the thread ID. That's all it's going to do, and threads don't need to return any value. So the main function is what sets this up. I define a number of threads. I define a pthread_t variable. This is a pointer to a thread array, and a pointer to an array of thread IDs. And then I allocate space with malloc, so they're stored on the heap, which can be accessed by every thread, an array of pthread_t's, which are pointers to threads, and thread ID numbers down here. And so now I assign them each an ID. I just start at 0 and count up 1. And then I create the threads. This is what creates a thread. You tell it where to store the pointer indicating to the thread. And null is some parameter about the type of thread. Here's the code to run in the thread, and here's where the thread ID is, which is the parameter to pass to that function. So it will call this function with those parameters and allocate it this thread number, this thread pointer. That's the game. So this will launch the threads. The threads will now run independently. And when they're done, the join command down here will wait for them all to finish. And from this point on, the program will be single-threaded again. So the only threaded part of the program is from here down to here. It creates the threads, and down here it waits for them all to finish, and then lets you see what happened. Then it's going to free them and come back. So that's what it does. And if you run it, clear, it's just .threads1. And I got to tell it how many threads. So if I run it with one thread, it just has one world, one called 2. Here's 2 threads. There's 4 threads. And there's no limit. There's 16. Now, one thing that's interesting to notice is they don't all come in order. 0, 1, but this is 0, 2, 3, 1. And when I have 16, you can see more clearly they all come in out of order because they do run independently. And they each get the processor in its wisdom. The operating system decides when to give them a slice of time, and there are other things going on in your operating system, other background processes, so they may not all finish in the order in which they were launched, not at all. So that's an important fact. You don't know what order they're finishing in, and that's going to lead to trouble as we go ahead. So that's the game. We've already talked about this, pthread join. All right, and that's the thread order. So now we can consider the second case for scalar multiplication. And this time, we haven't have a length here. All right. Oh, and I'm trying to remember what was different about this one. We're going to go down here. Assign each thread its own chunk of elements. Oh, that's right. This previous one didn't do anything. That's right. This one here just printed a message showing the different threads. Now what we're going to do is scalar multiplication. So let me look at the raw code here. I got to get back to the right window. Here we are. There. So clear. And cat threads2.c. All right, so this time we're going to actually do a task. So we're going to define a length, which is something like 1 billion here to make it slow enough so we can measure the time. And then we're going to have some global variables to keep track of things like the number of threads and such. And then this is going to be a scalar multiply. This is going to be a thread function. So each thread is going to go in here, it's going to know its ID number, and it's going to use its ID number. Now the goal is to take every element of this array and just multiply it by a constant. So it's going to pick a chunk of the data to use based on its thread ID, and then from start to end, it's going to multiply it. And then it's done. That's what's going to happen here. And that's going to be done with multiple threads. So down here, we have the same stuff we had before. We define a pointer to the thread array. We read the number of threads from command line. We allocate space for the thread array and the thread IDs, and then we create the threads with the thread array, This null, I forget what it does, something normal. I think you always leave null there. And then this scalar multiplies the function, and these are the parameters. So this will create a bunch of threads, and each one of those threads will independently multiply the numbers in a bunch of those arrays. Then I'll join and come back. So that's the game. So now if I run that one, threads 2, again I have to tell it how many threads. So if I run it with one thread, then it takes a little bit of time. So to find out what's going on, there's a nice command for this, and I put it in the slides, and that's it. Curly brace time to, when we get that here, and maybe I can make it fit on the screen so I can type that mess in. This is the cool way to measure the time. Use curly brace time, and then in here, threads 2 for one thread, and then 2 greater than ampersand 1. That will take the standard error, which is where the answer of time goes, and send it to standard out. And for some reason you need the curly braces, so you can then grep it to something that will just show the real time, is all I care about. That's the clock time. So this will tell me the clock time it took, and I'm fouled it up somehow. What did I do wrong? Oh, I need a semicolon. There. So it runs, and I can see how long it took. Okay, so it took 2.6 seconds with one thread. Now if I make 2 threads, it's 1.2 seconds, and 3 threads is 1.0 seconds, and 4 threads is 0.87, so it seems to be helping. And you see that here. More threads improve it. Now, you might wonder, how many will it keep improving? Will I try 4 and then 8? And then 16? It doesn't get any better. Now that would make sense because how many cores do I have anyway? Let's do ls CPU. And this will show you that I have one socket with 4 cores per socket and no hyperthreading. So I only have 4 cores. So having more than 4 threads doesn't do any good. If I have 8 threads or 16 threads, they still only go on 4 cores. So you'll get an improvement up to 4 and no real improvement after that. Now, if it were in a perfect world, it would get 4 times faster, but as you can see, it's not that good. 2.6 went down to 1.3, and this did not go down to like 0.6, it went down to 0.8 because there is some overhead in the thread switching, so you don't get as much improvement as you might imagine. All right, so now we can try, now they say global variables are considered a poor practice in C, so if you want to avoid them, you define a structure, and then you define all the values of the arguments up here in main, and then you pass the structure into the threads. So you populate the thread arguments for all the threads here, and when you create your threads, you're just going to pass that structure in here. So instead of having a global variable, it's in main, and it gets passed as a parameter to threads, which just passes a pointer in, and that is, I think, considered to be more efficient than global variables. All right, so we're down to some cahoots. Let's try these. Let me bring them up. This is 14A1. All right. Good. may not have any more than 2 today. We will carry on. All right, so which one has 5,000 cores frequently? Yep, that's the GPU. Good. All right, so a portion of a process that can execute independently. That's a thread. Good. And what function terminates all the threads? Join. Create creates them, and then join will end them all, and after that you're back to single threading again. All right. All right. All right. So then the issue comes of synchronizing threads. And here, there are 4 methods available. We'll talk about them. These are ways to handle controlling so threads don't undo each other's work. Mutex, semaphores, barriers, and condition variables are all ways to do it. And so let's consider this task. We're going to do a sort. I had a whole class full of sorting routines last semester. There's a sort we didn't use. I don't imagine this one's terribly efficient, but it's one kind of sort. So suppose you have an array of many items, but the items are actually drawn from a smaller set of possibilities. So each item only goes from 0 to 9, and there are 15 of them. So you want to sort this. What we're going to do is count how many times each value occurs. So if you look at here, there's 3 zeros, so you put a 3 there, and this will be how many 1s there are, of which there are 2, and here's how many 2s there are, of which there are 3, and so on. So you get the counts. Now you just rebuild the array. Put in 3 zeros, 2 1s, 3 2s, no 3s, 2 4s, 1 5, and so on. This is one way to do a sort. And it's just something we're going to try parallelizing. So let's take a look at it. That is count sort, and I should have it ready to go. Let's do clear and ls, and I've got it, so I can cat count sort .c. All right, so first let's take a look at the program here, and this count sort is going to be from your textbooks. They actually put the timing inside the program, which is more professional than my technique of using time outside. And so they've got an error handler and a helper function that creates the array and so on, and something that prints the array and something that prints the counts. All of that is not too important. Here's the thing that actually does the count elements. So it's going to go through the array, and it's just going to, for every possible value, it's going to read the value and increment it. So this is it's going to read each element, and whatever value it finds there, it's going to increment the count of that element and read to them one by one. So if there's n elements, this will do n calculations in this loop. That's what it does. And now it's going to write that out, overriding the original array to put the output, and that's it. Here's the main function. So this is a simple method of doing it, which does not use threading. All right. So that's the thread version, the unthreaded version of it. Now to make it a threaded version, you change it to this, the parallel version. You pass in an argument structure, and then you get the arguments out of here, which is going to be a pointer to the array and a pointer to the counts variable array that you're going to put the answer in. And then this has changed. This is, I'm afraid this is Apple AI. It tried to change my word to a word I don't understand. Count elements. All right. And so down here, it's going to do the same thing. It's going to go from start to end, count them and add them to the array. The only difference is, just like before, the one we did earlier, it's going to calculate a chunk of data to work on. Instead of doing the whole array, it's going to take the number of threads and calculate from its ID number and calculate which portion of the data this thread should work on. Okay, so that breaks the job up into separate pieces and runs the separate pieces in different threads. All right. And so the result is, that's count LMs here. And I did it, but I'm not sure I did it on this machine. Let me see. All right, let's see what happens if I run this one. Okay, count sort NP, N is the length of array. Right, this one is, the length of the array is 15. And the number of possible value, and 1, I want to print it. So there you are, 15, doing it this way. So there's the array before the sort, the array after the sort. So it works. Now, I don't think I have one live that's threaded. Oh, it's threads 2. Now I remember. I thought I did, just forgetting my naming system. So that's cat threads 2. There. All right. So this is the count sort. Yep, it gets a chunk. And no, it's not. This is the multiplier. All right. Anyway, I'm not going to worry about it. I think it's on my other machine, countlms.c. Let me just see if I made it so we can download it here from my server. I'm afraid I didn't. So I'll show you the static pictures anyway. So here's what happens when you run it. It may be that I didn't make it just in your book. I've forgotten. But anyway, here's the point. When you run it with one thread, then you get numbers. Now, it's a billion elements in 10 possibilities, so you get about 1 million in each one. So that's reasonable. But now if you have 2 threads, you only get 600,000 in each one. If you have 4 threads, you only get 500,000. So this program doesn't even get the right answer. The multiple threads, let aside time, it doesn't get the right answer. Now this is really bad. If your program doesn't even work, who cares about efficiency? And the problem here is a race condition. In the single-threaded version, you have this. This is the active ingredient where you add 1 to the count. The problem is this statement that looks like one line of code turns into several lines of code in assembly language. And so it turns into something like this. First, read the current value of this count variable and put it in a register, add 1 to the register, and then write the register back down. This is the assembly code that's created to do that line. And the problem is it could execute like this. The first thread could read it and put it in the register, and then increment it by 1. Now another thread could come in, read it, and put it in their register, and increment by 1. This one overwrites with the contents. This one overwrites with the contents. And depending on if this reads it, see here, it reads the stored count. So if the count was 10, and this one finds another occurrence to change it to 11, this one, it's going to try to write 11 here, but this one is going to have read 10, and also increment by 1 and get to 11. So even though there were 2 occurrences of the thing you're counting, you only incremented it by 1. Because the second thread undid the work of the first thread. This is the problem, and this is why you have to have a more carefully written program with locks. Same thing happens in databases, by the way, something I used to do decades ago. You'd have a giant database in a room full of people answering phone calls, and if 2 people would try to change the same record at the same time, you'd have the same problem. Like when two people could call in trying to change the address of an account, and you get a garbled address mixing the two, so we had record locks. So the first person that started modifying something, that record was locked, and the next person would not be able to modify it until they were done. It's the same issue. All right, so what you want is you want an atomic operation. This is in the old Greek sense of an atom. An atom is supposed to be the thing that cannot be divided. It's the smallest element. So an atomic operation, like updating that count, should be an atomic operation. It should either be done completely or fail completely. But there shouldn't be any condition in which it's halfway done. That's what you want. So what you're going to do is isolate the critical section of code and make it execute atomically. And that's down here. It's really this statement. All right, so you want it to be like this, where one thread reads the count, increments it, and writes. And it's not until that's done that the next thread reads it, increments 1, and writes. You want them to be each uninterrupted at doing this important task. and then you'll get an accurate count. So you can do it with the mutex. The mutex is there for this purpose. I've been hearing about them for years and using them in Windows as indicators of compromise for infections. I'm really glad to learn more about what they're for. A mutex is a global variable that every thread can see, and they can use it to do this job. It's basically like a record lock in databases. So you define a mutex globally, and then you can have a mutex lock, which means your thread will now wait until it can get a lock on the mutex. So it has to wait until everybody else is done using this. Then it gets a lock. Then it can do its job and unlock, and no other thread is allowed to run on this code until this is done. This is what you want. This way nobody can get interrupted. That turns all this code into an atomic transaction, an atomic operation, I guess. In cryptocurrency, by the way, this comes up. In cryptocurrencies I've studied and taught about, you also want to have an atomic transaction. If you purchase something in a cryptocurrency, you send currency to the other person, you get the reward, and the same thing can happen there. If those two operations can be split, you might end up paying for something without getting it, or getting it without paying for it. So they design atomic transactions, where there is one transaction where you pay for it and get the thing you purchased. That either succeeds or fails completely. No halfway is printed. All right, so mutexes are unlocked by default, and so you, in main, you initialize the mutex, and then you create the mutex. There's a separate mutex for each thread, and you run all your threads, and then you join them. That's the game. I'm going to be more careful than that. You create it here. But there's the same, only one mutex shared by all the threads. That makes me feel better. It has to be. So the mutex is initialized here and destroyed here, and the threads run, and each one of those threads will check that mutex to wait until it's their turn to process the data. All right. So now, when you run it, you get the right answer all the time, about 1 million of each one. So that fixes the problem. That fixes the accuracy problem. However, there's another problem. If you look at the timing, with one thread, it's 0.3 seconds. With two threads, it's 0.4 seconds. With four threads, it's 0.5 seconds. More threads make the task slower, not faster. So we've completely undone the whole point of having multi-threading. And the problem is, this means only one thread can do all its work, then the next thread can do all its work, so we might as well have only had one thread. You haven't allowed two threads to run at the same time ever, while doing the important task, so we've undone the entire benefit of multi-threading. So that's a problem. So one possible solution would be, instead of doing the whole loop and locking it for the duration of the loop, you just lock it when you do this one statement, which is the problem, and then perhaps another thread will be able to come in here. And what happens when you do that is it's much worse. Now one thread, now it's accurate, of course, but when one thread takes 1 second, two threads now takes 10 seconds, because this locking is a slow process. So now what you've done is you've made it do many, many of these locks and unlocks, and that consumes more time than this addition would take, so you made your program worse than a single-threaded program this way. All right, so now what we have to do is, a better solution is, instead of constantly trying to change the global total, you make a local total. Each thread independently constructs its own local totals, and then at the end, you'll add the local totals into the main counts. So this part is really independent, and you don't have to have a mutex for it. You just have a mutex once down here where you add the final result of this thread to the total. So now you don't have a lot of unnecessary locks and unlocks, and you allow most of the work to be done in a multiple threaded way. And now you will achieve one thread is 0.3, two threads is 0.2, four threads is 0.1, like you expect. Now you actually save time. So that's a more clever way of using it. All right. So there's a few other issues. You can have a deadlocked thread. Consider a bank transfer application where we're going to have an account that has a mutex for each account that can lock it in a balance. And then we're going to have, you send money from this account to that account. So we lock the from account, we lock the true account, then we take the balance out of one account and put it in the other, and then unlock the two accounts. This is one way you might write the thread. And it'll work. All right, now the problem is, what if you have a lot of transactions and a lot of threads? what if you have this situation where one thread is sending funds from A to B, account A to account B, and another thread is sending funds back from account B to account A? What happens is the first thread locks its from account and succeeds, but the second thread locks its from account and succeeds. Now this thread cannot get the second lock because it's waiting for this thread to finish, and this thread can't get its second lock because it's waiting for that thread to finish. Now the whole program freezes up. And this is a real subtle issue, and this has happened to a lot of cloud services. This happened, I think, to Yahoo Mail a few years ago, where some people start reading other people's mail. This kind of thing can happen, where you have something that looks pretty good, you run it on like a test system and it runs well, but when you actually put it in production and millions of users are using it and it really gets busy, then problems appear that you didn't foresee, because they'll only happen in rare conditions like this that weren't in your test case. So that's a deadlock. So the way to avoid it is don't lock two mutexes. Lock one mutex at a time. So lock the from account and subtract the money, then lock the to account and add the money. Now there's not a condition for a deadlock. That's one solution here. But that's an issue, those deadlocks. So there's a couple other ways to use things that are a little different than mutexes in special cases. Semaphores. Instead of just having locked and unlocked, a semaphore can have a variety of values, 0 through R, where R is some kind of total. And this documents each time a resource is used. So this is if you have not an issue of locked or unlocked, you have only so many of something. Like you only have 10 of them, and when they're all used, you have to wait until one is freed or something. So every time you use it, it decrements it, and when it reaches 0, it will lock that thread until more become available. So you have a function that says, I'm now done using this resource of which I have only so many, and someone else can use it. All right. So you include semaphore.h, and then you declare it and initialize it here with the address of the semaphore, the default state, locked or unlocked, and whether to share with threads of a process or threads between processes, and you destroy it here. And so the wait function will indicate that a resource is being used and decrement the semaphore, and it'll block. If semaphore reaches 0, means you can't get one. So you're trying to get something of which there's only so many. Like you might have print jobs going to a printer, and you have a bank of 10 printers, something like that. So you say, is one available? And wait will wait until one is available. Then it'll run. And sempost indicates that you're done with one, and it's free and gets added back to the available list, so the ones that are waiting can go. So that makes sense. All right. Other things you can have are barriers. Barriers force all the threads to reach a common point in execution before they can continue. So you have define a barrier, you initialize it, you destroy it after use, and the wait function creates a synchronization point. So here's an example of this. You would have a barrier here. This is a forced synchronization point. So all your threads are starting work, but they won't proceed here. And here at the barrier, it's not going to let anybody proceed until all the threads reach this point. Then they will all move forward, and then they're done with the work. All right. And then there are condition variables that will force a thread to block until a condition is reached. So you can have whatever complicated situation you need. You initialize it with a condition in it and destroy here. And here you have your wait, which will wait for some condition. And we're using a mutex. So it'll wait until this condition variable reaches some desired value. And this is what causes the calling thread to unblock the thread that's waiting. So you can define a condition calculating whatever you want. And so here's an example of that, where you have, say, eggs and chickens. Your chickens are going to lay eggs, and the farmers are going to want to pick up the eggs, but they're not going to pick up the eggs until one has been laid. So you prepare it here with condition variables. You have a mutex and you have a condition, which goes to your condition called eggs. And you have a chicken thread. You create some chicken threads and some farmer threads. And you wait for them to exit, and then you're done in main. And the chicken thread is here. So it's going to lay some eggs. It's going to wait for some period of time until it's ready to have an egg. And the chicken is going to occasionally lay an egg with a delay between the eggs. And when it does, it's going to lock the total, add to the total number of eggs, and then unlock down here. But before it unlocks, it's going to send a signal telling the farmer to wake up. The farmer is waiting for the chicken to lay an egg. This is going to send a signal back to the farmer with the condition variable telling him I laid an egg. And the farmer is going to wait here. They're going to create, while the number of eggs is 0 and there's no eggs to collect, it will just wait for the condition wait. This will wait until an egg appears. And when an egg appears, then it will go harvest the egg. So that's the game. And again, it will lock the mutex up here. Okay. And free it here. And I'm not, yeah. All right. That's what's going to happen there. All right. So that's an example of that situation. Like I say, these normally mutex is enough, but you have these exotic things for the more complicated situations. And here's another one, broadcast, where you broadcast saying all the threads can move ahead. And all the threads wait until they hear the broadcast message. So these are other conditions. All right. That's what I wanted to show you. Let's try another Kahoot, which is this one. Ah, good. All right. All right. So what situation allows one thread to undo the work of another thread? That's a race condition, where there is a brief moment when an action will have an unexpected result. All right. And we'll have a hands-on project with those coming up soon. All right. All right. What term describes an operation that is always accomplished in a single uninterruptible step? That's an atomic operation. It cannot be divided. It either happens or it doesn't. There's no situation in which it gets only halfway. That's atomic. All right. All right. And what p-thread construct is unlocked by default and only allows one thread to lock it at a time? The mutex, the common one, the normal one you'd normally use. That's what it does. Only one operation can unlock it, one thread can unlock it at a time. So therefore, that thread can do something in an atomic fashion that is not going to be interrupted or modified by some other thread. So all right. Okay, so let me stop this recording.